Welcome to the UNV certification program. The topic of this video is basic knowledge of lens. After you have learned this course, you will understand the function and types of lenses and master the matching relationship between lens and sensors, as well as get familiar with relevant lens parameters such as focal length, the field of view, DORI, and aperture. Let's start with the concept of lens. The function of the lens is to collect the light signal from the subject and image it to the photosensitive area of the photoelectric sensor of the camera through a series of optical glass lenses, which is the eye of the camera. The working process of the lens can be understood as the following process. The lens collects light signals from the subject, then transmits them to the sensor through the optical lens for imaging. So, after the lens transmits the light signal to the sensor, how does the sensor image? And how do we choose the right sensor for the lens? The main function of the sensor is to make the photoelectric conversion. The lenses collect the light signal that will be focused on the sensor. Then the sensor will change the light signal into the charge signal that can be processed, similar to how the human retina converts light signals into neural electrical signals. Sensors have different sizes that can meet different imaging requirements, and the common sizes are as follows. We can see 1 inch, 1/2 inch, 2/3 inch sensors, etc. Please note that this size does not refer to its length, nor its width, but the sensor's diagonal length. So speaking of this, you may have a question. Isn't 1 inch 25.4 millimeters? Why is it 16 millimeters here? This is actually caused by historical reasons. Back then, people started to use sensors in the 1950s, but the sensors at that time were different from those that are popular now. At that time, they were made of vacuum tubes, and there was a section of glass behind the vacuum tubes. So the sensor's length of 1 inch includes the glass behind it. In fact, its effective length is 16 millimeters with the glass behind it excluded. Therefore, with the development of the industry, 16 millimeters has gradually become the industry's default 1 inch. How do we match the right lens for sensors of different sizes? For example, here is a 1/3 inch sensor. We have 3 lenses to choose from. First, we try a 1/4 inch lens, we put it on and we find that it doesn't cover the entire frame, so the image will be like the picture on the right, with black borders. Then, if we use a 1/2 inch lens, it can completely cover the picture, but because the lens is too large, it also causes a lot of waste of the field of view. Next, we use this moderately sized lens and find that it is just right, so the one that fits is the best. Next, let's learn about the relevant parameters of the lens. First, let's take a look at what focal length is. As shown in the figure, the lens is a set of optical glasses. When the lights that parallel to the main optical axis pass through the lens, the lights converge to a point. This point is called the focal point, and the distance from the focal point to the center of the lens is called the focal length. So what's the use of focal length? How does it affect the imaging effect? According to the imaging principle of light, we can see that the focal length, the sensor size, the object distance, and the width of the captured object will form a group of similar triangles, so we can calculate how far a camera can see according to the focal length. Some cameras are fixed lenses, which means their focal lengths are fixed. While others are zoom lenses, when we try to increase the focal length, we will find that we can see farther, but at the same time, the field of view becomes narrower. So this is the relationship between the field of view and the focal length, and they are inversely proportional. From this picture, we can see that as the focal length becomes longer, the field of view of the lens becomes narrower and narrower. For example, when the focal length is 16 millimeters, we can only see things clearly at a close distance, but our field of view is very wide. And when the focal length is 200 millimeters, we can see distant things clearly, but our field of view is noticeably narrowed. Next is the relationship between focal length and DORI distance. For an object of 180 centimeters, when the pixel size is 40, it can be detected, when the pixel size is 100, it can be observed. When the pixel size is 200, it can be recognized. When the pixel size is 400, it can be identified. The object distance is equal to the focal length multiplied by the object length, divided by the pixels occupied by the length of the object. In addition to the focal length, there is another important parameter that affects the imaging effect of the lens, which is the aperture. Different scenes have different lighting environments. Sometimes the sky is brighter, and sometimes it is darker, so the amount of light entering the lens is different. The light may be either overexposed or not enough. Therefore, people invented the aperture, which is a device inside the lens. It can adjust the size of the light hole to control the amount of light entering. Its unit is f, which is the ratio of the focal length f to the clear aperture d. That is to say, the larger the clear aperture, the smaller the f. Apertures can be divided into fixed apertures and variable apertures. The picture on the left shows a manually adjusted variable aperture. There are also some apertures that are fixed, which means that the amount of light entering them is fixed. We can see that in the same scene, the imaging effects with different aperture sizes are very different. When the aperture is larger, the picture is brighter. When the aperture is small, the picture is darker. Finally, after understanding the basic concepts and parameters of lenses, let's take a look at how lenses are classified. There are two common classification methods for lenses. One is classified by aperture type. As we mentioned before, the aperture can be divided into the fixed aperture and the variable aperture, and the variable aperture can be divided into the manual aperture and the auto aperture. Manually adjusting the aperture is rarely used now as it requires rich operating experiences. The auto aperture is mostly used in PTZ cameras, which can automatically adjust the amount of incoming light according to the image quality. The other one is classified by focusing type. As we showed earlier, there are fixed lenses and zoom lenses. Zoom lenses are divided into manual zoom and motorized zoom. Compared with manual zoom lenses, motorized zoom lenses can be adjusted remotely, are easier to operate, and are also beneficial to save labor and maintenance costs, so currently, they are widely used. In summary, in this course, we've talked about the function and types of lens, the matching relationship between lens and sensors, the relevant lens parameters such as focal length, field of view, DORI, aperture. That's all for the basic knowledge of lens. Thanks for watching. See you next time.